Lasers by Illan Kunik, Daniel Farb, and Amanda Atzil. First, we are going to talk about the history of lasers.
Before the laser was created, there was the maser. Maser stands for microwave amplification by stimulated emission of radiation. Laser stands for light amplification by stimulated emission of radiation. In 1954, Charles Townes and Arthur Shallow created the maser. The difference between the maser and the laser is that masers use microwaves and lasers use light. Since light is visible and microwaves are invisible, masers are invisible and lasers are visible. In 1958, Townes and Shallow studied the possibility of a visible maser, the laser. Instead of using microwaves, it would use visible light. They did not continue studying the laser. In 1959, Charles Townes and Arthur Shallow were granted a patent for the maser. The maser was used to amplify radio signals and as an ultra-sensitive detector for space research. The ruby laser was created by Theodore Maiman. This is believed to be the first light laser ever. It's called a ruby laser because the medium of the laser is ruby crystal. Some believe that Gordon Gould created the light laser before Maiman. Gordon Gould was the first person to use the word laser. There is good reason to believe that Gould made the first light laser. He was a doctoral student at Columbia University under Charles Townes, the co-inventor of the maser. Gordon Gould was inspired to build his optical laser starting in 1958. He failed to file for a patent for his invention until 1959. As a result, Gould's patent was refused and his technology was exploited by others. It took until 1977 for Gordon Gould to finally win his patent war and receive his first patent for the laser. Ali Javan created the gas laser in 1960. The gas used in the gas laser was helium neon. Gas lasers were very useful and successful. In 1964, a gas laser that used carbon dioxide was created by Kumar Patel. The excimer laser was invented in 1970 by Nikolai Basov. The excimer laser is a form of ultraviolet laser which is commonly used in the production of eye surgery and micromachining. The term excimer is short for excited dimer. The correct but less commonly used name for such is exiplex laser.
Mechanisms. How lasers work.
There are two key characteristics about the laser. The light stays in a single beam rather than spreading out, and the light is only one color, as opposed to white light, which is a combination of colors. The reason the laser light can stay in one straight line is that mirrors and lenses are used to point the light in one direction. The reason that the light is one color is a bit more complex, though. A property of electrons is that after being energized, they will fall back to their ground state and emit light. The laser excites many electrons at once and has them leak a light of one color. However, in order to fully understand how a laser works, there is more to learn. There are two necessary steps that a laser must go through. The first one is population inversion. Population inversion is when more electrons are in a higher energy state than in a low energy state. In other words, all the atoms in the laser must be excited simultaneously. The second step is stimulated emission, which is the release of energy from the excited atoms by artificial means. Usually in nature, atoms or electrons become excited by being hit by discrete packets of light called photons. However, in a laser they must be excited without the use of photons first. One way to do this is to pump electrical energy into the atoms. The electric energy is pumped into the atoms when the button on the laser is pushed. Once all the electrons are excited, they will try to move back to their ground state. In doing so, the electron will release a photon as it lowers its energy level, and that photon will hit the electron of another atom. The atom that is hit will also release a photon, and a chain reaction of released energy will occur. In other words, the electrons will have achieved a state of stimulated emission.
To make a laser, all you need to do is give a big collection of atoms enough energy so they're excited and ready to emit light. Once one of them spontaneously emits a photon, it'll stimulate some of the others to do so, and you get a nice cascade of illumination. But instead of letting all the light escape, it's more powerful to trap it between two mirrors and let it bounce back and forth through the atoms. All that passing light will stimulate them to emit even more light, and as long as you keep on re-exciting the atoms, they're happy to go on emitting light forever. But why do the atoms emit light just because another photon passes by? It's actually pretty simple. Imagine flipping two coins. They can either be in the same state or in different states. But photons aren't like coins. No matter how hard you try, you can't tell one apart from another. So in a photon flipping experiment, that means there's only one way for them to be in different states, but two ways for them to be in the same state. So they're more likely to be in the same state. And in general, this implies that photons always want to be like other photons, to have the same phase, polarization, and go in the same direction. And what's more amazing is that if a solitary photon passes by an excited atom that could emit another photon, there's a good chance it will emit one, because the two photons want to be together, even before the second one exists. So once you have all these friendly photons bouncing around between the mirrors, you can just open up a little hole at the end and let out a blinding stream of coherent light. A laser beam.
In the video, the speaker discussed how photons want to be like other photons, which makes them coherent. To have coherent light waves, the crests of one wave are aligned with the crests of the other, and the troughs of one wave are aligned with the troughs of the other, as shown in the diagram. This also explains why the light of a laser is a single color. In this diagram of a laser, it shows the electrical pump, the reflecting mirrors, and the lasing material. The lasing material is what contains the atoms that need to be excited. Usually, the material is a crystal, gas, or dye. The diagram also has a transmitting mirror, which is the small opening that points the light in one direction.
It can be very complicated to understand the quantum mechanics involved in lasers, but by breaking it down into steps we are able to see how lasers work. Next, we are going to talk about the modern-day relevance and uses of lasers. There are lasers in use all around us that we don't even realize. There are lasers in your CD player and the CD-ROM in your computer, as well as in smoke detectors throughout your houses and in buildings. Very powerful lasers are used in machine shops to cut and weld metal. Because the light of a laser travels straight, lasers are used for many types of alignment and measurement. Construction workers now routinely use lasers to level floors and to ensure a stripe painted on a wall is straight. NASA left a mirror on the moon during one of the Apollo missions, which they bounce a laser off of to measure precisely how far away the moon is from the Earth. Medically, lasers are used for cosmetic surgery, which can be the removal of tattoos, scars, stretch marks, sunspots, wrinkles, birthmarks, and hairs. Lasers are also used medically in eye surgery. In tattoo removal, lasers are one of many methods that can be used. Laser treatment causes tattoo pigment particles to heat up and fragment into smaller pieces. These smaller pieces are then removed by normal body processes. A Q-switch laser is used in the procedure. Laser eye surgery is a medical procedure that uses a laser to reshape the surface of the eye. The military uses lasers for things such as targeting and firearm sighting. For firearm sightings, a small laser is mounted on top of some sort of gun or firearm. Most commonly, either a red or green laser beam shoots out of the laser when turned on. This beam is used to target objects. A small dot the color of the laser will appear on the object when the firearm is faced at it. This makes it easier to know when you are aiming correctly at your target. The military also uses something called a laser target designator. Infrared lasers, which are not easily detectable, are used to indicate a target for a precision-guided munition. The munition aligns itself with the laser in order for it to hit the precise location targeted. The scientific uses of lasers can range from the use of lasers on spacecrafts to astronomy, laser cooling, and nuclear fusion. Laser cooling is where you shine particular wavelengths of laser light at the ions or atoms, slowing them down, thus cooling them. As this process is continued, they all are slowed and have the same energy level, forming an unusual arrangement of matter known as a Bose-Einstein condensate. In astronomy, lasers have been used to create artificial laser guide stars, used to reference objects for adaptive optics telescopes. The industrial use of lasers varies from using lasers to cut and weld as well as barcode readers. The laser beam can be further focused to a microscopic dot of extremely high energy density for welding and cutting. The automobile industry makes extensive use of carbon dioxide lasers with powers up to several kilowatts for computer-controlled welding on auto assembly lines. Supermarket scanners typically use helium neon lasers to scan the universal barcodes to identify products. The laser beam bounces off a rotating mirror and scans the code, sending a modulated beam to a light detector and then to a computer which has the product information stored. The National Ignition Facility thinks they figured out how to cause more energy than what was put into a reaction to come out of it. They are currently trying to figure out why this happened and how it is possible. If the right answers come out of their research, they could potentially recreate the first energy source that renews itself. With more and more research being done to further advance laser technology, new ideas and inventions are being created every day. Over less than 100 years, we have gone from the maser to the various forms of lasers and their uses today. Who knows what lasers can be created and invented in the years to come?